Welcome to the video lesson on mathematical expectation, also known as expected value. And in this video, we'll talk about what mathematical expectation is, some key terms, and how to use it in a calculation. So first up, mathematical expectation is a measure of, on average, how much you would expect to win or lose in a game of chance. And the formula is complicated looking, but really what this means is that we're adding up the product of the probability of a given outcome times the value of that outcome. So probability is P and Q is the quantitative value, the net gain or the net loss. And I'll show you what I mean by that. But first up, a few key terms. If the mathematical expectation itself, if it works out to be a negative number, that interpretation is that on average, if you played enough of a certain game, you would expect to lose money on that game. And if the NE is positive, which is rare, this rarely happens in real life, it would mean that on average you would expect to win money on an average play of that game. And if the mathematical expectation is exactly equal to 0, that is what we call a fair game. And again, just to be clear, that doesn't mean that the probabilities of winning and losing are equal, but it means that the combination of the probability of winning times how much you win, the value, and the probability of losing and how much you lose, that combination makes it equal to 0. That's what is considered fair. So here's an example. Suppose you pay $2 to roll a single six-sided die, and then the game works as such. If you get an even number, you lose your money. If you get a 1, you get your money back that you bet. If you get a 3, you receive $3, and if you rolled a 5, you would receive $5. So if we're going to work out the mathematical expectation here, the question in a case like this, because there's a bunch of different outcomes, there's a bet amount, there are win and loss amounts, you would be asked, what is the mathematical expectation of this game? And remember that we had that complicated formula, but what it really means is to break down all the different outcomes. So in this case, there are, even though you could roll 6 different numbers on a six-sided die, there are only actually 4 different value outcomes. You could either get an even number, you could roll a 1, a 3, or a 5. So in total, there are 4. And what I do is I multiply the probability of each of those outcomes times the value of that outcome. So for instance, the probability that you get an even number is 1 out of 2. And the value, it says, is losing your money, which was 2. That's negative 2. Whereas the probability of getting a 1, there's 1 out of 6 numbers, and the value is to receive back my money. So if I bet $2 and I get back $2, my net amount, my value, is 0. There's a 1 in 6 chance of getting a 3, and the net value of that, if I get $3 back but I bet 2, my net value is plus 1. And finally, if I get a 5, there's a 1 out of 6 chance of that. The probability is 1 out of 6. And my net value is 5 minus the 2 that I bet. So if I fill those in with numbers, probability of an even is 1 out of 2, it's 1/2, or 3 out of 6. The value is negative 2. There's a 1 out of 6 chance of getting a 1 whose value is 0 because I get back my money. There's a 1 out of 6 chance of getting 3 minus 2, which is 1, because I received 3 but I bet 2. And there's a 1 out of 6 chance that I profit 3, 5 minus 2, because I received 5 and bet 2. And now to figure out the value of the mathematical expectation, I would combine all of these together, simplify them, multiply, and then add. And it works out that overall, the mathematical expectation here is equal to negative 1/3. And that means that even though negative 1/3 isn't one of the outcomes of the game, it means that if you played the game enough times, on average, that would end up being the average amount of my loss of playing this game. So it means that on average, you would expect to lose this game. And on average, you would expect to lose 1/3 of a dollar every time. That doesn't mean that each time you are going to. Of course, there's a probability that you win. There's even a probability, we could calculate it, that you win $5 twice in a row. But overall, if you played enough, that is what your average amount of the game would work out to be. We had mentioned also that if a game was fair, it had a mathematical expectation of 0, and that comes up in problems as well. For instance, here, if you pay $2 to play a lottery and your probability of winning is 1 out of 100, and it says that the lottery is fair, how much would you win if you won that lottery? So the fact that it says it's fair has a very specific meaning in this topic. Being fair means that the mathematical expectation is 0. So remember that mathematical expectation is adding up the product, the multiplication, of every outcome times the value of that outcome. So the first thing to do is to read through the problem, figure out the gist of the game, and figure out how many different payment options or outcomes there are. And in this case, there are only 2. Either you win or you lose. So here my mathematical expectation will be the probability of a win times the value of a win, plus the probability of a loss times the value of a loss. And we can add in this case, the fact that the game is fair means that the ME, the mathematical expectation, is equal to 0. The problem told us that our probability of a win was 1 out of 100, and my profit amount, my net win, is going to be whatever this is, the win amount, but I have to subtract 2 because I paid $2 to get the lottery ticket. And in every other outcome, all other 99 out of 100, in all of those cases, I just lose, which means I gave up the $2 that I paid. I end up with a net amount of -2. So if I work this through, I would first probably combine this together. And then I could move this to the other side to isolate the x. And then I would multiply both sides by 100. This is now just a little bit of algebra. And when I isolate the x completely, I get 200. And that means that win amount in that lottery would have to be exactly 200 for the lottery to be fair. And it means that if the win amount was anything more than 200, that the mathematical expectation would be positive. It would be sort of worth it to play. And if the win amount was anything less than 200, means that the mathematical expectation would be negative, and it would not be worth it to play that game. And one final example, here it says an amusement park offers a game of chance. There are 12 congruent or equal sectors. If the pointer stops on a white sector, contestants win the amount of money indicated and keep the money that they bet. If the pointer stops on a shaded sector, the contestants lose the money that they bet. And it says again that the game of chance is fair. The question is, what is the bet amount? So as opposed to the previous one that asked for the win amount, here is asking how much you would have to bet. So there are 12 sectors. We know that the game is fair. If you land on a white sector, you keep that amount and you keep your bet. So in my mathematical expectation, as I'm scanning through and trying to get a gist of the game, I want to know how many different payment outcomes there are. There's shaded, or I lose, that's 1. There's $4, $6, or $12. There's a total of 4 outcomes. And we know that the mathematical expectation is 0. We'll be able to put that in. But my outcomes are the probability of shaded times the value of shaded, the probability of 4 times, and the net amount. I just replaced the amount there. The value is 4. Because getting $4 and getting my bet back means that whatever amount I bet, if I also get it back, it cancels out. If I bet $10 and I got 4 and my $10 back, the 10 that I bet and the 10 that I got back cancel out. My net profit is 4. Same for the 6. If I got my bet back, it cancels out. And same for the 12. My bet cancels out. So I know that my mathematical expectation or expected value is 0, and I can replace all the probabilities just by counting them out. If there are 12 sectors, there are 6 shaded spots. And if you want to pause and count out the other ones to replace those probabilities, go ahead. I'll replace them now. And if the only thing that I'm looking for is this bet amount, because it's unknown, but I know that I'm going to lose my bet, I only have one unknown left in the problem. And so I can solve that by doing a little bit of algebra. I'd isolate that x, I'll move everything else to one side and group it together. And when I solve, that x turns out to be 6. It means that in this case, I would bet $6 for the game to be exactly fair. And if I had to bet less than $6, it means that the mathematical expectation would be positive. I would be expected to win over time. And if the bet amount was anything bigger than 6, then this would work out to be a negative mathematical expectation game, a losing game overall on the whole on average. Thanks for watching.